Hello, I hope you guys can hear me. Let me just set up my chart. Also, I'm going to be doing another derivative stream. Last time I started with L'Hopital's rule. Gonna continue that today. Okay. Yeah. So last time I started reading this. It's basically L'Hopital rules says limit as x approaches a, f of x over g of x. This fraction is of type 0 over 0. So basically when the limit approaches a, both of them are reaching 0. Then this is equal to limit x approaches a, derivative of f over derivative g a. There. So this is true for 0 over 0 case, and this is also true for infinity over infinity case. But they didn't provide the proof for the infinity over infinity part. For type 0 over 0 and for type infinity over infinity. Okay. Other indeterminate forms. I think I was here last time. L'Hopital's rule is very useful for evaluating limits involving the indeterminate forms 0 over 0 and infinity over infinity. However, we can also use L'Hopital's rule to help evaluate limits involving other indeterminate forms that arise when evaluating limits. The expression, wait, hold on. The expression 0 times infinity, infinity minus infinity, 1 to the power of infinity, infinity to the power of 0, and 0 over 0 are all considered indeterminate form. These expressions are not real numbers. What about 1 to the power of infinity? Isn't that 1? Rather, they represent forms that arise when trying to evaluate certain limits. Okay, indeterminate form of type 0 times infinity. Suppose we want to evaluate a limit as x approaches a, f of x times g of x, where f of x approaches 0 and g of x approaches infinity as x approaches a. Since one term in the product is approaching 0, but the other term is becoming arbitrarily large, anything can happen to the product. We use the notation 0 times infinity to denote the form that arises in this situation. The expression 0 times infinity is considered indeterminate because we cannot determine without further analysis the exact behavior of the product f of x times g of x as x approaches a. Okay, as x approaches infinity, f of x approaches 0 and g of x approaches infinity. However, the limit as x approaches infinity of f of x f of x times g of x varies depending on n. If n is equal to 2, then the limit is 3. If n is 1, then the limit is infinity. Evaluate x from the right side, x from the positive side, x times ln of x. We see that limit ln of x approaches minus infinity as x approaches 0 from the right side, and 1 over x approaches infinity as x approaches 0 from the right side. Therefore, we can apply L'Hopital's rule and obtain, we conclude that the limit is 0. So basically we do the inverse of this and then we check which form it is. Another type of indeterminate form is infinity minus infinity. Consider the following example. Let n be a positive integer and let f of x is equal to 3 times x to the power of n. G of x is 3x squared plus 5. As x approaches infinity, f of x approaches infinity and g of x approaches infinity. We are interested in limit as x approaches infinity f of x minus g of x, depending on whether f of x grows faster, g of x grows faster, or they grow at the same rate. As we see next, anything can happen in this limit. Since f of x is approaching infinity and g of x is approaching infinity, we write infinity minus infinity to denote the form of this limit. Right. But I need proofs for the infinity over infinity part and infinity minus infinity part. Uh, As with other indeterminate forms, infinity minus infinity has no meaning on its own, and we must do more analysis to determine the value of the limit. For example, suppose the exponent n in the function f of x is equal to 3x to the power of n is equal to 3, then the limit is infinity. On the other hand, if n is 2, then the limit is minus 5 because these two cancel out. If it's 1, then it's negative infinity because this grows faster. So we can only evaluate to see by seeing which one grows faster, right? Which one grows faster here? Is it 1 over tan x? I think it's this one. So it would be negative infinity, right? Wait, this must. Let's see. One over tan x grows faster than 1 over x squared, right? But they both grow to infinity. We need to check whether their difference grows to infinity or not. Another type of indeterminate form that arises when evaluating limits involve exponents. The expressions 0 to the power of 0, infinity to the power of 0, and 1 to the power of infinity are all indeterminate forms. On their own, these expressions are meaningless because we cannot actually evaluate these expressions as we would evaluate an expression involving real numbers. The indeterminate form 0 to the power of 0 and 1 to the power of infinity can be handled similarly. We proceed as follows. Let y is equal to f of x to the power of g of x, then ln of y is ln of f of x to the power of g of x, which is equal to g of x times ln of f of x. Since limit as x approaches a of f of x is infinity, we know that limit of x as x approaches a of ln of f of x is also infinity. Therefore, this limit is of the indeterminate form 0 times infinity, and we can use the techniques discussed earlier to rewrite the expression g of x times ln of f of x in a form so that we can apply L'Hopital's rule. Then, okay, we can take the limit. This is infinity to the power of 0. And let me see. This is infinity. And this is 0. So for this, limit as x approaches infinity, ln of y as x approaches infinity ln of x over x. Wait. 1 over x. We have an infinity over infinity form, right? So we can just take the derivative of this. Derivative of ln of x is 1 over x. Derivative of x is 1. So 1 over x. So then we use this ln. We switch the limit and ln infinity y 0. So that means e to the power of 0 is 1. So x and sin x and x, they both approaching 0 from the right side. So let's see, limit as x approaches 0 from the right, x to the power of sin x. So limit as x approaches 0 from is 0. Sin x is also 0. So 0 over 0 form, we do y is equal to sin x ln of y is equal to ln of x over sin x, and so we take the limit sin x ln of x. We this also limit. Oops. So this is infinity times 0 case. Isn't sin x, wait, I need to find out the trigonometric functions. This will go to negative infinity. This will go to 0, so it's 0 times negative infinity case. What if we do the inverse? What if we ln as x approaches 0 sine x divided by 1 over ln of x. Now this approaches 0 and this approaches infinity, I think. What if we do 1 over sine x? Let's do that instead. Arc sine x. Okay. So we have negative infinity over infinity, right? Now we find the derivative of this. Derivative of ln of x is 1 over x. I think it's better if I write it like this. And then derivative of the outside, sine x minus sine x to the power of minus 2 and times the derivative of the inside. Derivative of sine x is cos x. So minus wait. This is correct, right? One is equal to sine square x plus cos square x. Sine square x is equal to cos square x minus 1. Does this make sense? Now if I do cos x, this top part is approaching 0, right? Even with sin x, this top part is approaching 0. But the bottom part is also approaching 0. So do we derivate it again? Am I doing something wrong? Oh, they did 1 over ln of x. Or over here they did cosecant. So in the first option, what they did, and they reached here. Now they tried the second option. Cosecant x cot x, using the fact that cosecant x, we can rewrite this. Wait, I think I reached here, right? Yeah. Hold on. I needed to check I was on the right path. I don't wanna spend hours on the wrong direction. So minus sine x, this, and then sine over cos is tan x over x. This approaches 0. What about this? Tan x over x. Tan x over x. This approaches 1. Okay, I need to write it down here. So what are the things I need to write? I'll just save it. Not bad. Okay, I need to fix this. Fix this. I need to write identity for 1 over sine x so I can have it in my website. I thought I had written this. Oops. Apparently I did not. So x, I think it would be easier if it's on this side. Now this derivative is 1. This goes to 0. And then e to the power of 0 is 1. Growth rate, growth rates of functions. Comparing the growth rates of ln of x squared and e to the power of x. They used L'Hopital's rule to evaluate this limit, and they concluded that e to the power of x grows faster than x squared. Okay, for the following exercises, evaluate the limit. Let's do one of them. Copy and close. Um, So this goes to infinity, but that depends on what case. If k is 1, if k is equal to or more than 1, then the limit is infinity. If k is less than, wait, if k is more than 0 and less than 1, then not equal to 1, sorry. Zero, because x will get smaller. If k is equal to 0, x to the power of 0 is 1, then x to the k is 1. Negative. What happens negative 1? Uh, this is negative 1. It becomes 1 over x, right? It becomes, so if it's like 0. minus 0.05. That's the same as saying like this, 1 over x to the power of 0.05. Wait a minute. Wait, I think I did a mistake here. Even if it's... No, hold on. This is wrong. It has to be if k is more than 0. If k is less than 0, then x would be at the bottom, right? Then it would be 1 over x to the power of something. If x goes to infinity, then this will be 0. So either we have infinity over infinity case, okay, or infinity over 0, or infinity over 1. Then x, this implies the total limit let's call this L. The limit is infinity. So if k is more than 0, derivative, and then the derivative of this. X to the power 0.5 the power of k. Wouldn't e to the power of what's the answer? I need to know the value of k though. So answer key chapter 4. If k is 1, then we have infinity over infinity case all over again. No, I mean, if k is 1, then if k is more than 0, if k is more than 1, this would be positive, right? But then we have the infinity over infinity case all over again. I think if k is 1 or less than 1, then e to the power of x would outgrow it. Let me think this through. Three, five, seven. It just says infinity. I mean, it's not always going to be infinity. It depends on the value of k. Should I do next chapter? What does t mean here? Wait, hold on. Let's do one question. Um, let's do 401 maybe. So and it goes to pi sine. So 1 plus cos x and sine x. To 0 and -1. This is 1 plus cos x. So it's 0 and 0. We have a 0 over 0 case, then we find the derivative of each. Derivative of 1 is 0. Cos x is minus sin x. Sin x is cos x. Now we have a problem. This is negative tan x. Which would be 0, right? So this is 0. This is what? 401? Yeah, 0. Okay. In many areas of pure and applied mathematics, we are interested in finding solutions to an equation of the form f of x is equal to 0. For most functions, however, it is difficult, if not impossible, to calculate their zeros explicitly. In this section, we take a look at a technique that provides a very efficient way of approximating the zeros of functions. This technique makes use of the tangent line approximation and is behind the method used often by calculators and computers to find zeros. Consider the task of finding the solutions of f of x is equal to 0. If f is a first degree polynomial, f of x is equal to a of x plus b. Then the solution of f of x is equal to 0 is given by the formula x is equal to minus b divided by a. If f is a second degree polynomial, the solution can be found using the quadratic formula. However, the polynomials of degree 3 or more, finding the roots of f becomes more complicated. Although formulas exist for third and fourth degree polynomials, they are quite complicated. Also, if f is a polynomial of degree 5 or greater, it is known that no such formulas exist. For example, consider the function. No formula that allows us no formula exists that allows us to find the solutions of f of x is equal to 0. Similar difficulties exist for non-polynomial functions. For example, consider the task of finding solutions of tan x minus x is equal to 0. No simple formula exists. In such cases as these, we can use Newton's method to approximate the roots. Newton's method makes use of the following idea to approximate the solutions of f of x is equal to 0. By sketching a graph of f, we can estimate a root of f of x is equal to 0. Let's call this estimate x0. We can then draw a tangent line to f at x is equal to 0. Or they're guessing x, a value of x where f of x is equal to 0. So where f of x is equal to 0. So the first guess is x of 0. If this is not 0, then Then this tangent line, let's call this as, we draw a tangent line to f at x is equal to 0. Draw a tangent line. Anyway, that tangent line touches, that's x1. Typically, x1 is closer than x is equal to 0 to an actual root. If the graph is like this, we make a guess over here and then draw a tangent line. If this is bigger, if x1 is bigger than x0, then we make another guess for x0, but on the other side of the thing, of the maxima or minima. This tangent line intersects the x-axis at some point, x1, 0. Now let x1 be the next approximation to the actual root. If this is the case, draw tangent line y is equal to draw a tangent line at x, y, the place, point where tangent line touches is touches the x-axis. X1 is the next guess. Repeat above steps. Now if x1 is not 0, then we draw a tangent line at f of x1 and see where that tangent line touches x2. Now let's look at how to calculate approximations x0, x1, x2. So x0 is our first. So y is equal to normally in a graph. So what I'm imagining, we have y is equal to mx plus c, where c is the y-intercept. if you have a function, you want to find the tangent line here. The gradient is this. This is the gradient. Normally, if it's like if we draw y is equal to x0 x plus c, then we get this line. The gradient is the same as this, and c is whatever the y-intercept is here, but instead we shift this line here. We 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 shift this line, so now it's y is equal to f of x0. Now it's shifted, so it's x minus x0. So this is x0. We shift it this many times. And before it was plus c, now it's plus plus this. Now this is the intercept. So since we have this tangent line, we can set y is equal to 0 and find this x value. And this would be our next guess. Solve this equation for x is equal to 1. We conclude that x1 is equal to x0 minus f of x0 divided by the derivative of f at x0. And for x2 we do this, for xn we do this. So xn is equal to the old xn minus this over the derivative. Next, we see how to make use of this technique to approximate the root of the polynomial f of x is equal to x cubed minus 3x plus 1. We have to find all of this. So, let's take this. Let's paste here. But why did paste not work? So f of the derivative of f of x is 3x squared minus 3. So x0 is 2, x1 is x0 minus f of x0 divided by the derivative. So 2 over here. What's this? Let's see. 2 cubed. Is it cubed? Yeah. 2 cubed minus 3 times 2 is 6. Wait. Yeah. This one, 3. So we have 3 here. The derivative of 2, 2 times 2 is 4, 4 times 3 is 12, 9. Now what? x1 is 2 minus 1 over 3. This is 5 over 3. 5 over 3. Let's see if we got our x1 correct. Yes. Should we do the rest? We know that we obtain the same value of x5 and x6. Therefore, any substitute application of Newton's method will most likely give the same value for x and finding a square root. Typically, Newton's method is used to find roots fairly quickly. However, things can go wrong. Some reasons why Newton method might fail include the following. At one of the approximation of xn, the derivative f is 0 at xn, but f of xn is not 0. As a result, the tangent line of f at xn does not intersect the x-axis. Therefore, we cannot continue the iterative process. I guess we can like shift a little bit forward or backward. The approximation x0, x1, x2 may approach a different root. If the function has more than one root, it is possible that our approximation does not approach the one we are looking for, but a different root. The approximation may fail to approach the root entirely. We provide an example of a function and an initial guess x0. So it's this. Example 4.48. Let's set x0 is equal to 0. If x0 is equal to 0, then it will reach a different root, right? This goes to 1. Or you may get stuck in a loop, right? Other iterative process As mentioned earlier, Newton's method is a type of iterative process. We now look at an example of a different type of iterative process. Consider a function f and an initial number x0. Define the subsequent numbers xn by the formula xn is equal to capital F xn minus 1. This process is an iterative process that creates a list of numbers. This list may approach a finite number as n gets larger, or it may not. Let x0 is 0. Okay, so we solve this for x0 and the solution would be x1. Then we solve this for x1 and the solution would be x2. Okay, iterative processes can yield some interesting behavior. In this section, we have seen several examples of iterative processes that converge to a fixed point. We also saw in example 4.48 that iterative process bounced back and forth between two values. We call this kind of behavior two-cycle. Iterative processes can converge to cycles with various periodicity, periodicities, such as 2 cycles, 4 cycles, where the iterative process repeats a sequence of 4 values, 8 cycles, and so on. Some iterative processes yield what mathematicians call chaos. In this case, the iterative process jumps from value to value in a seemingly random fashion and never converge or settle into a cycle. Although a complete exploration of chaos is beyond the scope of this text, in this project we look at one of the key properties at chaotic iterative process, sensitive dependence on initial conditions. This property refers to the concept that small changes in initial conditions can generate drastically different behavior in the iterative process. Probably the best known example of chaos is Mandelbrot set, after named after Benoit Mandelbrot, who investigated its properties and helped popularize the field of chaos theory. In this project, we use the logistic map r times x and multiplied by x1 minus x as a function in our iterative process. Yeah, I don't want to read all that. Should I do exercises next stream? Yeah, I think I will do this next stream. Okay, I guess I'll end the stream here then.